Can you hear me? Yep.
Okay, great. So the next speaker is Yunchong Wang, who's going to talk about SAGA survey and the universe machine.
So hi everyone. Want to thank the organizers for squeezing in this last-minute talk, and I'm glad to share with you what we're learning about dwarf galaxy star formation and also their quenching in the SAGA survey with this empirical framework universe machine that's actually developed by Peter Baruzzi, also in the room. So I like to start with this graph that Yimeng showed earlier, that this is sort of our understanding of galaxy-halo connection across all halo mass scales that host galaxies in the universe, and perhaps the least constrained and most poorly understood part is in the dwarf galaxy low mass end. And you can see if you extrapolate all of these empirical models down to very low masses, they have huge scatter and predict, orders of magnitude difference in like what dwarf galaxies live in what halos. So when I started grad school, this is when Peter's new empirical modeling framework, universe machine, came about, and Risa told me, let's just apply this to zoom-ins. I got the zoom-ins part. We need high resolution to actually resolve substructures that host dwarf galaxies in the universe. But why universe machine? So to summarize, it's really hard to summarize this complicated model in one page, but what it actually does is to have a parameterized star formation rate mapping from halo properties onto galaxies, and to make it flexible enough such that you can constrain the model with observations. So a step further from traditional abundance matching that only maps between halo mass and some halo galaxy observable, this model also considers assembly history as a secondary bias that predicts difference of SFRs in halos of fixed mass, and you map lower SFRs onto halos with lower accretion rates. So essentially with this two halo parameter model, you can paint SFRs onto a cosmological dark matter only simulation, integrate over time, and forward model stellar catalogs. And you can predict things like stellar mass functions, quench fractions as a function of stellar mass, and galaxy clustering. So essentially you do this all redshift matching self-consistently with a population of mock galaxies that's forward modeled from that's anchored on dark matter halo merger trees. And the key assumption that's being tested here is, to what extent does these two parameters, halo mass and assembly, capture and describe galaxy evolution? So if you read the very short paper that Peter wrote in 2019 that's only 52 pages long, you will find that actually it's remarkable that these two parameters, halo mass and assembly history, describe galaxy evolution at masses above 10 to the 9 pretty well over a wide range of cosmic history from redshift 8 to 0. And obviously, before we actually constrain this model and see if we can describe dwarf galaxy formation with this framework, is to test if this assumption based on these two halo properties are still valid to describe galaxy formation at these lower masses below the LMC mass scale. So what we did in the first step was, without any new data, we just extrapolate this model, apply it to zoom-in simulations that go down to halos that's below the atomic cooling limit of 10 to the 7, and ask, okay, what do we find actually when we compare the MINT model that's only constrained at higher masses, and potentially we will identify model limitations. And by doing so, we also can establish a cosmological framework that places dwarf galaxies together with their more massive counterparts in a cosmological context. So this is actually what we found by just applying an unconstrained version of universe machine in this mass range to the zoom-ins. So that's shown in the blue. And as you can see, that this model actually lies in between a lot of these four orders of ignorance we see in among other models. But if you compare the blue specifically with the gray band in the background, that's an abundance matching results that's informed by the latest observations of Milky Way satellites from DES and Pan-STARRS, led by Ethan Nadler, former student in our group, now at Carnegie. And we really know that, okay, our just out-of-the-box stellar mass-halo mass relation is somewhat reasonable, given latest observations. But how did the dwarfs actually get onto this stellar mass-halo mass relation? So if we look at ultra-faint dwarfs here on the right, predicted by the model in the stellar mass range of 10 to the 4 to 10 to the 6, in these two mass bins, and compare to these resolved star formation histories from Dan Weiss 2014, which is based on color magnitude diagrams of HST observations, our predicted star formation histories are crazy. These ultra-faint dwarfs form half of their stars since redshift 0.5. This doesn't totally make sense. And if you look at the halo accretion history of these dwarf galaxies, these dwarf halos, the late-time star formation isn't really driven by halo growth. So it's just that the model extrapolation doesn't work. The parameters are totally messed up. And we were able to identify the key problem that's with the model when you extrapolate it down to these mass scales. It's really that when you look at the quench fraction as a function of stellar mass, when you go down to masses below 10 to the 8, it's just an extrapolation that asymptotes to 0. And the model assumes everything, all dwarf galaxies in the universe, are star forming since they were born, which is obviously not the case as we see in local dwarf galaxies. So on the left, these are observations. In the purple band, that's field galaxies. They are mostly star forming, down to stellar mass of 10 to the 7.5. But obviously, if you look at satellites around Milky Way mass halos, that's obviously not the case. They shouldn't have a quench fraction of 0. A significant portion of them are star forming. So I'm not an observer. Sorry, that's 2 slides from now. Before moving on to observations, we really need an update to the model to allow flexibility to actually let the model be constrained by data. So obviously, we want to have a non-zero quench fraction at stellar masses below like 10 to the 8.5 to allow dwarf galaxy quenching at these mass scales. But also, we know that this is not just a mass effect. The model also cares about the different assembly histories of halos. That will actually affect when you have an overall quench fraction at some fixed mass. The correlation strength between SFR and halo assembly will create differences in quench fractions of different subhalos, essentially in Milky Way-like environments and like field environments. This difference, this offset from the mean quench fraction will differ. So you need to also free up these things to be jointly constrained by the new data. So I'm not an observer and speaking for our observer team here, but this is sort of the landscape of all local dwarf galaxies that live in a Milky Way halo. The farther distance you go out, the less dwarf galaxies you observe in each host. The closer you are, the less hosts you are able to sample, and you will be able to know less about differences in host environments. So what we're doing is we're taking the satellites around Galactic Analog Survey, SAGA, about 400 satellites, over 102 hosts. This is a spectroscopic survey, unlike ELVS, which is a photometric survey, combined with field dwarfs in Marlockey 2012 from SDSS, and see that how dwarf galaxies actually come from mostly star-forming population in the field and quench as they come into a Milky Way masked halo. So a little more on the data update. So we are on the verge of releasing SAGA 3, and the survey team has finished the spectroscopic survey around 102 hosts. Instead of the stage 236 hosts, we've expanded our satellite collection from 127 to almost 400. And most importantly, we have updated SFR measurements that combines H-alpha equivalent width with Galax and UV fluxes. We have better understanding of our spectroscopic completeness. We're quite good above stellar masses, above 10 to the 7.5. And in the silver sample between 6.75 and 7.5 on the right, we think we have a better, more confident completeness correction to our spectroscopic incompleteness that's also color magnitude based. So we basically calibrated our model onto the corrected SAGA sample, which represents satellites around Milky Way mass halos, and also jointly with the field galaxies with similar stellar mass but truly isolated in the field. So here is what we actually find. This is very preliminary. This is a work that I'll be leading that will be part of the SAGA 3 data release, but mostly there are 2 takeaways. So halo mass in assembly history, which is basically the universe machine framework, seems to largely capture dwarf galaxy quenching around Milky Way mass host. And if you look at the solid curves here, the model is able to capture the drastic difference in quench fractions between the SAGA satellites and the mostly star-forming field galaxies. And this process represents how these dwarf galaxies quench as they enter a Milky Way halo. And secondly, what we also notice as being very interesting is that the model seems to predict a limited difference between the satellite quench fractions, the red curve, and the blue curve, which is the field, when you go to masses below 7.5. And this has interesting implications about how satellites quench environmentally. So we did this numerical experiment with our model where in the top panel we can actually artificially remove this secondary bias, this correlation between SFR and halo assembly. And if you do so and you only make the model mass dependent, then there won't be any environmental correlation between satellite quenching. So you will see that the field population and the satellites in Milky Way hosts will have exactly the same quench fraction as the overall quench fraction as all mass scales. So that's clearly not the case, and the bottom panel represents what the data tells us. So you really need a very strong correlation between SFR and halo assembly to explain the difference, the drastic difference in the quenching of satellites around Milky Way mass halos. So secondly, what we really understand from the exercise here is that the halos themselves between field and a Milky Way host setting don't differ that much theoretically from lambda CDM, and their halo masses and assembly histories have finite difference that caps their difference in allowed for quenching. So what this implies is that if you really extend this model down to 10 to the 6th, where there are absolutely no observations yet, 60% of the field halos need to quench before they come into a Milky Way mass setting to account for the 90% quenched objects at 10 to the 6th within the Milky Way. Otherwise, halo quenching or environmental quenching alone via halo stripping isn't enough. So if something like DESI-LOSI in the future observes that field quench fractions are only 20% in the field at 10 to the 6th, then you will have to invoke other mechanisms that dominate satellite quenching at these mass scales. So I put my summary here, and I just want to highlight that we're also working on a reionization model to model ultra-faint dwarfs in the Milky Way and M31 with resolved star formation histories that goes to much lower masses, and we're also working on a set of embedded disk simulations that produce much more realistic subhalo populations to conduct this empirical modeling framework. So thank you for your attention.
Questions?
Great talk. We know that in hydro simulations and Dirac meta-only simulations, the subhalo mass functions are different. While universe machine is based on Dirac meta-only simulation, would that be a problem for you?
Yeah, I mean, that's why we are actually running embedded disk simulations to start with, because probably down to these dwarf scales where they live in M peak or MV or larger than 10 to the 10, it's less of an issue. But if you really look at these abundance of ultra-faint dwarfs in the center of halos, that's where it starts to matter. So my answer to that is to actually use embedded disk simulations to capture baryonic effects.
I see. Thanks.
Great talk, thanks. So you showed maximal assembly bias to reproduce SAGA at low mass n.
Right.
Which brings the high mass n data point in the worst
Yeah.
position. Can you comment on that?
Yeah, so that's a very good question that I didn't talk about. So the reason why we need an RC of 0.5 is really supported by clustering data at stellar masses above 10 to the 10.5. And what happens is that this model still agrees with the existing data set. It's just that when you look at the SAGA data point here, SAGA seems to have a quench fraction that's lower than the expected theoretical prediction. And we still don't understand why this is the case, but I think this can relate to the fact that this delta V max parameter doesn't characterize short time scale and small distance variations in like these strong tidal fields near tidal forces near pericentric passages. And ultimately, this could lead to a need for an update to the entire framework.
Very interesting. Glad to hear that SAGA is nearly finished.
Thank you.
But something that I'm puzzled by, all of your plots are looking at quench fraction as a function of stellar mass, doesn't the distance from the central galaxy play an important role? You were sort of alluding to that. The closer the satellite gets to the center, the stronger the tidal force, the denser the gas is, and therefore the stronger the ram pressure stripping. But I didn't notice any discussion of that.
Yeah, so I really didn't have time for it, but I can show you a peek into the plots that actually we do use the quench fraction as a function of distance to host as a constraint. So what we're finding is that in the lower mass bin from like 7 to 8.5, it does a reasonable job. It doesn't capture the innermost bin. But this mass bin above 8.5, like what Arthur asked just now, this is totally overestimated. And we think that the model is inflexible enough in this mass range. So like this is where we are, and yeah, happy to talk more about this.
Okay, great. So we're about 10 minutes behind the schedule. So we'll meet at 3:45, 30 minutes from now. Let's thank all the speakers this session.